Before we talk about ionic solids, let's review the concept of enthalpy. Enthalpy is effectively a measure of heat flow. We give the symbol delta H to enthalpy. Delta meaning change in, and H representative of enthalpy. Later on this semester, we'll talk more about a formal definition for enthalpy and where it comes from. What's going to be important for us is that we can distinguish between exothermic and endothermic processes. We have said that an exothermic process results from heat leaving a system. Exo like exit. Enthermic indicating heat. Any process whose enthalpy is exothermic will produce heat. A system gives off heat to its surroundings through an exothermic energy change. Mathematically, we describe the enthalpy for this system as being negative. Anytime a process is exothermic, delta H is less than 0. In other words, delta H is negative. It has a negative quantity value. The opposite of this is an endothermic process. In an endothermic process, heat is applied into a system. A system takes in heat, and it will feel cooler than its surroundings. We can describe the enthalpy change associated with an endothermic process as being a positive value. Delta H is greater than 0. Delta H is positive. We'll use these concepts to describe energies for both ionic bonds and covalent molecular bonds. We've discussed so far that elements like to form bonds so that they can reduce their overall energy state because they're lazy and don't want to have any more energy than they absolutely require. For ionic bonds, we can visualize the energy process or energy flow associated with the formation of an ionic bond through what's called the Born-Haber cycle. This cycle is going to be a visual depiction of how an ionic bond forms from its constituent elements, taking into account things like ionization energies and electron affinities. As a case study, let's think about the formation of lithium fluoride from its constituent elements, lithium and fluorine. Lithium fluoride has the formula LiF. To balance this reaction, we just need a half equivalent of diatomic fluorine. To visualize this, we're going to think about an initial state where we have separate lithium and fluorine in their elemental forms. Later on, eventually, these elements will come together to form the compound lithium fluoride. This is our final state. If we think about energy as increasing upwards along this visual depiction, then initially, the standalone elements are in higher energy states than the final product of this formation of an ionic bond. There are several things that we must do to get from the initial state to the final state. Hypothetically, we need to get our lithium to vaporize, then ionize. We need our fluorine to gain an electron, and then we need to have our lithium ion and our fluoride ion come together to make lithium fluoride. The first step must be lithium vaporizing. This process requires an input of energy. It's an endothermic one. The specific amount of energy depicted in this arrow is called the enthalpy of vaporization. Its symbol is delta H VAP. The next thing that will need to happen now that we've vaporized the solid lithium is to ionize that lithium. Remember, the first ionization energy is described as a gaseous phase neutral substance losing an electron to form a positively charged cation. This process also requires energy, and the quantity of energy required is given by the first ionization energy for lithium. The next step we might recognize needs to deal with fluorine. Fluorine in its elemental form is diatomic, but notice that we only have one fluorine anion necessary for the lithium fluoride compound. So we need to break a bond between two fluorine atoms in the diatomic molecule, F2. To break a bond, we need to input energy once again, and the quantity of energy amounts to the bond enthalpy that held two fluorine atoms together in the first place. We'll talk more about bond enthalpy in just a little while. The next step is going to be achieving two ions. We already have the lithium cation, but we need this extra electron that was produced through the ionization of lithium to attach to fluorine. We can describe the energy associated with that process through the electron affinity for fluorine. Attaching an electron to fluorine is going to reduce the overall energy of the system. At this point, we'll now have gaseous lithium cation and fluoride anion. But notice that our final product, lithium fluoride, is in the solid phase. There is one final step here, and that's the condensation of these gas phase cation and anions to the solid lithium fluoride ionic. This releases a tremendous amount of energy, this process in theory. The quantity of energy that is produced through this coalescence is referred to as lattice energy. The lattice energy of a solid specifies the energy requirement to transform 1 mole of lithium fluoride or any other ionic solid into its gaseous constituent ions. For lithium fluoride in particular, as for other ionic compounds, this lattice energy is huge. We give the symbol for lattice energy, delta H lattice. For this particular substance, the lattice energy is 1,050 kilojoules per mole. So when lithium fluoride forms from its constituent cation and anion, there is a release of 1,050 kilojoules for every mole worth of our final solid formed. This is an extremely exothermic process. Notice that the processes that got us in this cycle from our initial state to respectively ionized cation, anion, required an overall input of energy. The energy of our respective ions is higher for the gas phase components than either of our initial starting materials. It's this lattice energy that makes it worthwhile energetically for lithium fluoride to form in the solid state.